and welcome back to the Deep Dive. Today we're getting into something most of us probably use pretty often, maybe without even thinking much about the tech behind it. Ride-sharing apps, like Uber or Lyft.
Yeah, it's pretty amazing when you stop and consider it. Millions of people, drivers, all connecting in real time.
Exactly. Handling just vast amounts of data, getting you a ride quickly, safely. It just works. It seems seamless.
Uh-huh.
Okay, let's unpack this incredible feat of engineering that, we probably take for granted.
And what's really fascinating, I think, is we're going to go beyond just listing the services they use. We'll dig into the why these specific choices. It reveals a lot about building large-scale systems.
Right. So the mission today is basically laying out the architectural blueprint for building one of these things, production grade, super scalable, resilient, using AWS cloud tech.
And showing those specific, sometimes opinionated choices and trade-offs, turning this huge challenge into something you can really grasp.
Absolutely. And those first choices, the architectural ones, they're critical, aren't they? They kind of set the stage for everything else. Technology, how fast you can move.
Oh, completely. It's a strategic decision right from the get-go. And maybe the most fundamental one early on is monolith or microservices.
The classic debate.
Yeah. The traditional way, the monolith, it's one big code base. Simple to start, maybe, but for something like ride-sharing, it gets messy fast.
How so? What are the main drawbacks there?
Well, development slows way down. Everything's tightly coupled. If one part, say, location updates, gets hammered with traffic, you have to scale the whole thing. Super inefficient.
And a single bug can take down the entire app.
Exactly. Single point of failure. It becomes a liability.
Okay, so if the monolith is out for complex stuff like this, what's the alternative? What gives you that needed agility?
That's where microservices step in. Instead of one giant blob, you build it as a collection of small, independent services. User management, payments, matching. Each its own code base, often its own database, talking via APIs.
Right. And the big tech companies, they mostly went this way, didn't they? Even if they started monolithic.
That's the really interesting part. Amazon, Netflix, Uber itself. They all made that transition. Netflix is a great example. They needed microservices to handle their, explosive growth. It let teams deploy hundreds of services independently. Huge boost for reliability and speed.
So for our ride-sharing app, it sounds like microservices are pretty much the only viable path then. You get that independent scaling.
Yeah, location tracking needs to scale differently than user profiles.
And fault isolation, if the rating system hiccups, booking still works.
Crucial. Plus, team agility. Small teams focused on specific services can move much faster.
But it's not all sunshine and rainbows, right?
Yeah.
Microservices introduce their own headaches, don't they? There's always a trade-off.
Ah, you nailed it. That's the key insight. You trade monolithic complexity for distributed complexity. Now you have potentially dozens, even hundreds of services. How do they talk to each other reliably? How do you debug a request that bounces across 5 different services?
Right, sounds like you could end up with a distributed monolith if you're not careful, with everything making direct, synchronous calls to everything else. A new kind of spaghetti.
Exactly the trap you want to avoid. And the solution, generally, is an event-driven architecture, ED.
Okay, explain that. How does EG work?
Think of it like a central bulletin board. Instead of Service A calling Service B directly, Service A just posts an event like ride requested to a central message bus.
Okay.
Then other services, the consumers, subscribe to the events they care about. Matching service, ETA service, pricing. They all see that ride requested event and react asynchronously.
So they're decoupled. The service posting the event doesn't even know who's listening.
Precisely. It promotes loose coupling, increases agility, boosts resilience too. If the notification service is down for a bit,
It doesn't stop the payment service from working.
exactly. The payment service doesn't even know the notification service exists. It just reacts to payment events. Uber's architecture is a prime example of ED in action, handling massive scale efficiently.
It really highlights that building these systems is all about understanding trade-offs. There's no single perfect answer.
None at all. And a fundamental trade-off in distributed systems is captured by the CAP theorem.
Right. Consistency, availability, partition tolerance. You can only pick 2, essentially.
Well, sort of. Partition tolerance, meaning the system works despite network breaks, isn't really optional in the real world. Networks fail. So P is mandatory.
Which forces a choice between C and A, consistency or availability.
When a partition happens, yes. Do you choose consistency, a CP system, potentially refusing a request to guarantee the data is perfectly up to date? Think banking, you can't have inconsistent balances.
Or do you choose Availability, an AP system, always responding, even if it means data might be slightly stale from an isolated part of the system, like maybe social media feed updates.
Exactly. And the real insight isn't just knowing CVSA, it's understanding your specific needs. For our ride-sharing payment service, strong consistency is a must, no double spending.
Non-negotiable.
But for, say, updating a user's profile picture, eventual consistency is probably fine. If it takes a few seconds to propagate everywhere, who cares? That prioritizes availability and low latency.
So it's not one size fits all for the whole application.
Definitely not. There's a whole spectrum. Strongest is linearizability, like for payments. Then eventual consistency, like DynamoDB often uses. And things in between, like causal consistency, ensuring related operations appear in order, maybe for chat messages. A real production system is a hybrid, applying the right model where needed.
And what about handling growth? When load increases, how do you scale?
Two main ways, vertical or horizontal. Vertical scaling means beefing up a single server, more CPU, more RAM. It's simple initially, but hits limits, often needs downtime, gets expensive.
Right.
Horizontal scaling is the cloud way, scaling out. You add more machines to a pool and use a load balancer to spread the work. It offers, theoretically, near limitless scalability and better fault tolerance.
So our ride-sharing app needs to be designed for horizontal scaling from the start.
Absolutely. Across the board, compute, databases, everything.
Okay, so with those architectural principles, microservices, EBA, understanding CAP, designing for horizontal scale, let's get more concrete. How do we actually build the foundation on AWS, starting with, like, the network security?
Right. First step is setting up our digital perimeter using Amazon VPC, the virtual private cloud. It's your own private, isolated slice of the AWS cloud, full network control.
And you'd spread this across multiple availability zones for high availability.
Definitely. Multiple AZs are key for resilience. Within each AZ, we create public and private subnets.
Public for things that need direct internet access, like the load balancers.
Correct. They use an internet gateway or IGW.
And private for the back-end stuff app servers, databases that should never be directly exposed.
Exactly. They stay shielded, but they still might need to reach the internet for, say, software updates or calling external APIs.
How do they do that securely?
We use a NAT gateway. It lives in a public subnet, and the private subnets route their outbound internet traffic through it. The NAT gateway allows outbound connections, but blocks unsolicited inbound ones.
Gotcha. And route tables control all this traffic flow.
Yep. Public route table points to the IGW. Private route table points to the NAT gateway. Clean, secure network topology.
Okay, that sets up the basic network structure. But this raises an important question. How do you control what traffic is allowed between these subnets, or even to specific instances? How do you prevent unauthorized access within your VPC?
Layered security. We use two main tools here, network access control lists, NACLs, and security groups.
2 layers, how do they differ?
Think of NACLs as the outer wall around a subnet. They're stateless, meaning they check rules for both inbound and outbound traffic independently. They operate at the subnet level, are good for coarse-grained rules, like blocking a known malicious IP range entirely. Rules are evaluated in numerical order.
Okay, outer wall. What about security groups?
Security groups are like the inner gate, or maybe a security guard, right at the door of each individual resource, like an EC2 instance or a Lambda function. They're stateful. If you allow inbound traffic on a certain port, the return traffic is automatically allowed out, regardless of outbound rules. They provide fine-grained control.
Can you give an example of how they'd work together?
Sure. Your web server's security group might allow HTTPS traffic, port 443, from anywhere, 0.0.000. Your application server security group might only allow traffic from the web server's security group, and your database's security group might only allow traffic from the app server security group. The NACL at the subnet level might have broader rules, perhaps blocking certain ports entirely.
So it's defense in depth. If one layer is accidentally misconfigured, the other can still protect you.
That's the principle. It significantly reduces the chances of unauthorized access.
Okay, network security makes sense. What about securing access to AWS resources themselves? Managing users, permissions?
That's all handled by AWS Identity and Access Management, IAM. And the golden rule here is the principle of least privilege. Grant only the permissions necessary to perform a task.
Started with the main account access.
Right. Your AWS account root user. Lock it down. Strong password, multi-factor authentication, MFA. Remove any programmatic access keys. Use it only for tasks that absolutely require root.
And for everyday administrators.
Create IAM users for individual humans. Don't share credentials. Organize users into IAM groups based on roles, like developers, admins, and attach permission policies to the groups, not individual users.
Okay.
Much easier to manage.
Makes sense. What about applications or AWS services needing permissions? You don't want to hard-code access keys in the app, right?
Absolutely not. That's a huge security risk. The best practice, and this is critical, is using IAM roles for services. AWS services like an EC2 instance or a Lambda function can assume a role, which grants them temporary security credentials to access other AWS services they need. No hard-coded keys. The credentials expire and rotate automatically. Far more secure.
That handles AWS to AWS communication securely. But what about secrets within the application, like database passwords or API keys for third-party services?
Another common place people slip up hard-coding those secrets in code or config files. Big no-no.
So what's the solution?
AWS Secrets Manager. You store sensitive information like DB passwords or API keys as secrets. Your application, using its IAM role, gets permission to fetch these secrets dynamically at runtime from Secrets Manager.
So the secrets aren't in the code or deployment package.
Correct. And the killer feature, automatic rotation. Secrets Manager can integrate with services like RDS, our database service, to automatically change the password in the database and update the stored secret value on a schedule, say, every 30 days.
Without needing to redeploy the application.
Exactly. No manual intervention, no code changes. It drastically reduces the risk from potentially compromised credentials.
So what does this all mean for the security of our sensitive data? It sounds like layers upon layers.
It means we've built a strong foundation. Network isolation with VPC, granular traffic control with NACLs and security groups, strict access management with IAM roles and least privilege, and secure handling of application secrets with Secrets Manager. It's comprehensive.
Okay, secure foundation laid. Now let's start putting the actual application pieces on top. You mentioned a polyglot approach earlier, using the best tool for each specific job.
Yeah, that's key in microservices. No single database or compute type fits all needs. So let's look at the user and authentication services. These handle things like registration, log in the user-facing APIs.
Traffic here could be pretty spiky, right? Lots of logins around commute times, maybe quieter overnight.
Exactly. Unpredictable load. This is a perfect fit for a serverless first approach using AWS Lambda.
Serverless, meaning no servers to manage.
Right. Lambda functions run your code in response to events, like an API call. AWS handles all the infrastructure provisioning, scaling, patching. It scales automatically from 0 requests up to thousands per second, and you literally only pay for the compute time you consume down to the millisecond. Ideal for these synchronous API calls.
And how do users actually call these Lambda functions? Through API Gateway.
Precisely. Amazon API Gateway acts as the front door. It's a fully managed service that handles request routing, throttling, security, and monitoring for your APIs. We design a REST API, follow good practices like versioning in the URL path.
And idempotency, right? Especially for anything that costs money or changes state.
Critical. Using an idempotency key header allows clients to safely retry requests without causing duplicate actions, like creating 2 accounts or processing a payment twice. API Gateway also handles things like rate limiting to prevent abuse and input validation.
And it integrates directly with Lambda.
Yeah, using Lambda proxy integration, it basically passes the raw HTTP request directly to your Lambda function, giving you full control. For authentication itself, we'd use an industry standard like OAuth 2.0, probably implemented with Amazon Cognito, which handles user sign-up, sign-in, and token management.
OAuth being like that valet key granting limited access without giving away the master password.
Good analogy. And for authorization, what a logged-in user is allowed to do, we use JSON Web Tokens, JWTs. Cognito issues a JWT on successful login. The client includes this token in subsequent API calls.
An API Gateway can check if the token is valid.
Yes, it can validate the JWT's signature and claims locally without needing to call back to Cognito every time. That makes authorization stateless and very performant.
Okay, users sorted. Now the really dynamic part, location and matching. Millions of drivers sending updates constantly. You called it a fire hose earlier. How do you handle that sheer volume?
Yeah, a traditional database would just fall over trying to handle that many writes per second. This calls for a specialized ingestion layer. Apache Kafka is the tool for this job, and AWS offers it as a managed service called Amazon MSK.
Kafka, how does that help?
Kafka is essentially a distributed append-only log. It's built to handle massive throughput, millions of messages per second. Drivers, apps publish location updates to a Kafka topic. It just absorbs the writes.
And the persistence is key, you mentioned.
Crucial. The data stays in Kafka for a configured period. This means multiple different consumer services can read the same stream of location updates independently. Our real-time matching service reads it, maybe a separate analytics service reads it too, without impacting each other.
Okay, so Kafka catches the fire hose. But then, the core query. Find the 10 closest available drivers to this writer right now. How do you do that fast enough? A relational database scan would be way too slow.
Way too slow. Milliseconds matter here. This requires an in-memory solution optimized for this specific type of query. Amazon Elasticache or Redis is perfect.
Redis. I know it is a cache, but how does it handle location?
Redis has built-in geospatial data structures and commands. You use commands like GOADD to store driver locations, longitude, latitude, driver ID, in a sorted set. Then you can use georadius or geosearch to query for all drivers within a certain radius of a writer's location, and it returns results in milliseconds.
Wow, okay, so the matching logic, where does that run?
The matching service would be another microservice. It would likely run as a fleet of containers, maybe using Amazon ECS or EKS. These container instances consume ride requests from a Kafka topic, query Redis for nearby drivers using those geospatial commands, apply any other matching logic like driver rating, vehicle type, and then initiate the ride offer.
And you'd put a load balancer in front of these matching service instances.
Definitely. To distribute the incoming ride requests evenly, you might use an application load balancer, perhaps configured with the least outstanding requests routing algorithm to send requests to the instance with the fewest active connections.
Makes sense. Okay, let's shift to the absolute core, the ride and payment services. This is where transactional integrity is king. You can't lose a ride record or mess up a payment.
Absolutely non-negotiable. For this core transactional data, ride details, payment status, user driver IDs involved, we need a relational database with strong ACD properties, atomic, consistent, isolated, durable.
And the choice here, standard PostgreSQL or MySQL.
We'd likely go with Amazon Aurora. It's AWS's cloud-native relational database, compatible with both MySQL and PostgreSQL, but with significant performance and availability enhancements.
Like what?
Up to 5x the throughput of standard MySQL, 3x standard PostgreSQL. The storage layer is self-healing, distributed across 3 availability zones automatically. It supports up to 15 low-latency read replicas for scaling reads. Failover is typically sub-30 seconds. It's built for mission-critical workloads like this.
And how do you scale writes if one database instance isn't enough?
That's where database scaling strategies come in. Replication, using those read replicas, handles read scaling from day one. For scaling writes beyond a single instance, especially as you go global, you need to design for sharding.
Sharding.
Yeah.
Meaning partitioning the data.
Yes. Horizontally partitioning the data across multiple independent database instances. You might shard by regioned or maybe citied. A write happening in London goes to the London shard. A write in Tokyo goes to the Tokyo shard. This allows you to scale both read and write throughput almost infinitely. It adds complexity, but it's necessary for global scale.
So Aurora for the critical transactional data. What about other application data, user profiles, maybe driver details, historical ride info, stuff that doesn't always need complex relational queries or joins?
For data with simply access patterns, where you need predictable, single-digit millisecond performance at virtually any scale, Amazon DynamoDB is often a better fit.
DynamoDB, that's the NoSQL p-value and document database.
Exactly. Fully managed, scale seamlessly, great for things like user profiles, get profiled by userid, driver details, maybe storing historical ride summaries for quick lookups.
Is there a specific way to use DynamoDB effectively? I hear people talk about single table design.
Yes, that's a common best practice, especially for complex applications. Instead of creating many small tables, you design one main table, or maybe a few, using generic primary key, PK, and sort key, SK attributes. You then structure your data and create secondary indexes to support all your different query patterns efficiently against that single table. It avoids costly full table scan operations and optimizes performance and cost.
Interesting. So a hybrid database strategy using the best tool for the Aurora for transactions, DynamoDB for scalable key value access.
Precisely. Polyglot persistence.
Now notifications. A ride status changes, driver arriving, ride completed, and multiple things need to happen. Push notification to the rider, maybe an email receipt later, perhaps updating an analytics dashboard. How do you coordinate that reliably?
This is another classic use case for asynchronous event-driven patterns. We use the SNS to SQS fan-out pattern.
SNS and SQS, simple notification service and simple queue service.
Correct. When the ride service updates a status, it publishes one message to an SNS topic, say ride status changed.
Okay.
Then multiple SQS queues subscribe to that SNS topic. You might have a push notification queue, an email receipt queue, an analytics queue. SNS fans out a copy of the message to each subscribed queue.
So one event triggers multiple downstream actions, but they're decoupled.
Exactly. The ride service doesn't know or care about notifications or analytics, and SQS queues provide durability. If the email service is down for maintenance, its messages just wait safely in the email receipt queue until it comes back online. It doesn't block anything else. Real-time broadcast via SNS, plus durability and decoupling via SQS. Very powerful pattern.
And finally, the front end, the actual web app or the data source for the mobile app. Where does that live?
The front end is typically a single-page application, SPA, HTML, CSS, JavaScript. Since these are static files, the best place to host them is an Amazon S3 bucket, configured for static website hosting. It's incredibly durable and very inexpensive.
Just S3. Wouldn't that be slow for users far away from the AWS region?
Good point. To ensure low latency globally, you put Amazon CloudFront in front of the S3 bucket. CloudFront is AWS's content delivery network, CDN.
So it caches the website files closer to the user.
Exactly. It caches copies of your HTML, CSS, JS, images, etc. at edge locations all around the world. When a user requests your site, they get served from the nearest edge location, which dramatically speeds up load times.
You mentioned caching earlier, too, with Redis. It sounds like caching happens at multiple layers.
Absolutely. A good caching strategy is multi-layered. You have browser caching, controlled by HTTP headers, CDN caching, CloudFront for static assets, maybe API gateway caching for common non-personalized DIT requests, and then application-level caching using something like Redis or Memcache via Elasticache for frequently accessed data like active driver locations or session data. Each layer reduces load on downstream systems and improves latency.
Wow. Okay, so we've designed this complex distributed system, but designing is one thing. How do you actually build and deploy all these microservices reliably and repeatedly? Manual deployments sound like a recipe for disaster.
Oh, completely unmanageable and incredibly risky in a microservices world. Automation is not optional. It's fundamental for speed and safety. The foundation for automation is infrastructure as code, or IAC.
Defining your infrastructure and code files.
Exactly. We use AWS CloudFormation. You define all your AWS resources, VPCs, subnets, databases, Lambda functions, IAM roles, everything in declarative YAML or JSON templates. This template becomes the single source of truth for your infrastructure.
What are the benefits?
Consistency, repeatability, version control for your infrastructure. You manage infrastructure changes through code reviews and automated pipelines, just like application code. No more manual clicking in the console, which is error-prone. CloudFormation manages resources in stacks, logical units you can create, update, and delete together.
Are there best practices for using CloudFormation in production?
Definitely. Use parameters and mappings in your templates for reusability and environment differences. Always use change sets before applying updates. They show you exactly what CloudFormation will change, preventing accidental resource dilution or unwanted modifications. Enable drift detection to identify any manual changes made outside of CloudFormation. And for complex setups, use nested stacks to break down your infrastructure into manageable modules.
Okay, IAC handles the infrastructure. What about deploying the application code itself for all those microservices?
We need a robust continuous integration and continuous deployment CI/CD pipeline for each microservice. This enables teams to release updates independently and frequently.
What AWS services make up that pipeline?
Typically, you start with AWS Code Commit for source control. It's a managed Git service. Each microservice lives in its own repository. A push to the main branch or a merged pull request triggers the pipeline.
Then the build and test phase.
That's AWS Code Build. It's a fully managed build service. You define your build steps, compiling code, running unit tests, integration tests, building Docker images, and a build spec.iml file within your repo. Code Build executes these steps, produces artifacts like a Docker image, and can push them to Amazon ECR, the Elastic Container Registry.
ECR being the storage for your Docker images.
Right, like a private Docker hub. Then, AWS Code Pipeline orchestrates the whole flow. It connects the stages, source, code commit, build, and deploy. When code changes in code commit, Code Pipeline automatically triggers code build, and if successful, triggers the deployment stage.
And the deployment itself. How does the new code get onto the servers or Lambda functions?
That's handled by AWS Code Deploy. It automates deployments to various compute services like EC2, ECS, Lambda. Critically, it supports safe deployment strategies to minimize risk and avoid downtime.
Safe deployments, like blue-green.
Exactly. Blue-green is a common one. Code Deploy provisions a whole new environment, green, with the new version, runs tests, and then instantly shifts traffic from the old blue environment to the new one. If anything goes wrong, you can shift traffic back just as quickly. Minimal risk, zero downtime deployment.
Any others?
Canary deployments are also popular. You route a small percentage of traffic, say 5%, to the new version first. You monitor it closely using CloudWatch metrics and alarms. If it looks good, you gradually increase the traffic percentage until 100% is on the new version. This limits the blast radius if the new version has a subtle bug.
So separate, automated CI/CD pipelines for each service, using tools like code commit, code build, code pipeline, and code deploy with safe deployment strategies. That's the key to agility.
It empowers teams to own their services end-to-end and release value quickly and safely. It's core to making microservices work effectively.
Okay, we've built it, we can deploy it automatically. But launching is just the start, right? Production is a different beast. Things break. You need to know what's going on. Failures are, as they say, a when, not an if.
Absolutely. Especially in complex distributed systems, you need robust observability and efficient maintenance processes. It's about being prepared for failure, because it will happen.
What are the key components of observability? How do you get that visibility?
There are generally considered 3 pillars of observability. The first is monitoring, focused on metrics.
Metrics and numbers, like CPU usage, error counts.
Exactly. Quantitative data about system performance and health. AWS services automatically publish tons of metrics to Amazon CloudWatch. We use CloudWatch dashboards to visualize key metrics in real time. But crucially, we set up CloudWatch alarms.
For proactive alerting.
Yes. An alarm watches a metric and triggers an action if it breaches a threshold. For example, if the 5xx error rate on the payment API stays above 1% for 5 minutes, send a notification via SNS to the on-call engineer's pager. This lets us know about problems before users start calling support.
Okay, metrics tell us what is happening. What tells us why?
That's the second pillar, centralized logging. Logs provide the context, the narrative behind the metrics. In a microservices world, you have logs coming from potentially hundreds of Lambda functions, containers, servers. You need one place to collect and search them all.
And that's CloudWatch logs.
Right. We configure all our services to send their logs, application logs, system logs, to CloudWatch logs. Then we can search across all logs from a single interface. And CloudWatch Logs Insights provides a powerful query language to analyze log data, find all logs for a specific user ID across multiple services, count specific error types, etc.
Got it. Metrics for what? Logs for why? What's the third pillar?
Distributed tracing. This addresses a specific challenge in microservices. A single user request might flow through 5, 10, or more different services before completing. If that request is slow or fails, how do you pinpoint where the bottleneck or error occurred? Looking at individual service logs or metrics often isn't enough.
Right. You need to see the whole journey.
Exactly. That's what AWS X-Ray provides. You instrument your application code using the X-Ray SDK. When a request comes in, X-Ray assigns it a unique trace ID, which is automatically propagated as the request travels from service to service.
So each service adds its timing info.
Yes, each service records how long it spent processing its part of the request, a segment, and sends this data along with the trace ID to X-Ray. X-Ray then stitches all these segments together into an end-to-end trace for the original request.
What does that give you?
It provides a service map visualization showing the request path, dependencies between services, latency at each step, and error locations. You can immediately see, the request slowed down dramatically when calling the inventory service. It drastically reduces the mean time to resolution, MTTR, for complex issues.
So CloudWatch for metrics and alarms, CloudWatch logs for centralized logging and insights, and X-Ray for distributed tracing. Those are the 3 pillars.
That's your observability foundation for understanding system health and diagnosing problems quickly.
Beyond keeping things running, keeping costs under control is also huge in the cloud. Any key strategies there?
Oh, definitely. Cost optimization is an ongoing process. One big area is storage. For data that becomes less frequently accessed over time, like old ride records or logs you need for compliance but not daily analysis, use S3 intelligent tiering.
How does that work?
It automatically monitors access patterns and moves objects between different S3 storage classes like standard, infrequent access, archive tiers to optimize cost without performance impact for retrieval. You can also set S3 lifecycle policies to automatically transition data to even cheaper, colder storage like Glacier flexible retrieval after, say, 90 days, or even delete data after a certain period.
Smart. What about compute costs? EC2 Lambda.
Compute right-sizing is crucial. Don't just guess instance types or Lambda memory. Use CloudWatch metrics, CPU utilization, memory utilization, to understand the actual needs of your applications. Over-provisioning wastes a lot of money. Choose the smallest EC2 instance type or Lambda memory configuration that meets your performance requirements. Remember, Lambda cost is directly tied to memory allocation and execution duration.
Continuous monitoring and adjustment then.
It has to be. Cost optimization isn't a one-time task.
This has been incredibly thorough. We've gone soup to nuts on building a massive, complex system. For listeners who are inspired by this and want to build a career in cloud engineering, what's the path forward? How do you stay current and prove your skills?
Great question. The cloud moves incredibly fast, so continuous learning is absolutely essential. A few key resources.
Like what?
Definitely follow the engineering blogs of companies operating at scale. Netflix, Uber, Stripe are fantastic. They often share real-world challenges and solutions. And, of course, the official AWS architecture blog is invaluable for best practices and new service deep dives.
Any specific AWS papers to recommend?
The AWS well-architected framework is fundamental. It covers 6 pillars: operational excellence, security, reliability, performance efficiency, cost optimization, and now sustainability. Reading that and the associated white papers, like Microservices on AWS implementing blue-green deployments, gives you a solid conceptual foundation.
And for getting hands-on. Reading is one thing, doing is another.
Absolutely. AWS Skill Builder is a great starting point. Lots of free digital courses, and their paid builder labs let you work directly in a pre-configured AWS environment. Platforms like A Cloud Guru, Coursera, Udemy also offer excellent courses, often with labs or sandbox environments for practice. Getting your hands dirty is key.
Makes sense. And finally, certifications. Are they valuable? Which ones matter?
They are definitely valuable for validating your knowledge and demonstrating commitment to potential employers. There are different paths. For developers building apps, the AWS Certified Developer Associate is a good start, leading potentially to the DevOps Engineer Professional for CI/CD and automation expertise.
And for those focused more on design and architecture?
The AWS Certified Solutions Architect Associate is probably the most popular foundational cert, covering how to design secure, resilient, cost-effective systems. The Solutions Architect Professional is the advanced level, really digging into complex designs, migrations, and deep understanding of trade-offs across multiple services and accounts. It's highly respected.
It really is staggering how many layers, services, and careful decisions go into making something like a ride-sharing app just work. What a journey just exploring the blueprint. We touched on everything from the high-level shift to microservices and EDAs.
Down to securing the network with VPCs, security groups, IAM.
Making those specific tech choices like Aurora versus DynamoDB, Kafka versus Redis.
Automating everything with IAC and CI/CD pipelines.
And finally, keeping it all running smoothly with observability and cost management. It's a lot.
It is, which raises an important question, I think. What part of this comprehensive blueprint will you choose to explore first? Because the principles we've discussed here, they aren't just for ride sharing. They're pretty much universal building blocks for almost any large-scale distributed system you might want to build.
A really powerful thought. Your journey as a cloud builder, if you're interested in this stuff, has really just begun. Take this blueprint we've discussed, build on it, maybe even break it in places, and then rebuild it better. What problem will you solve next using these kinds of tools and techniques?